Hello, so my name's Colby Anderson, and in this video I'm going to show you, or I'm going to highlight my skills as a software developer. This video is going to be broken down into the following parts, so feel free to skip wherever. The time codes will be in the description. So the first part, I'm going to talk about why I'm choosing this specific project to showcase my software engineering skills, and the project will be GPS routing software, and you can find that on my GitHub. I'll also put that link in the description. The second part of the video, I will be going over the functionality that is intended for this project. The third part will be the showcase of the functionality. There's two user interfaces for this project, a GUI and a REPL. I'll be going over both, the REPL in less detail. The fourth part of this video, I'm going to discuss the overall architecture I designed for this project, and the fifth part will detail the implementation package by package, and within that I'll be going over the architecture of the package, the algorithms used, how extensible the code is, how general it is, and any optimizations I made. And then in the last part of the video I will be going over the tests that I made, both system tests and unit tests, or integration tests and unit tests. So the first part of this video, the purpose of why I chose this specific project. This specific project has many aspects of software engineering. It has test-driven development. Obviously you can't see the test-driven part because it's after the fact, but I'll be showing you all the different tests. It has lots of algorithmic complexity. For example, I do a star search, but in a particular way where it's loaded in dynamically from the database instead of the whole graph at once, like a common A star search. I have a KD tree that I use and a few other cool algorithms. There's also a lot of architecturally complex things I did in this project. It's also very general and extensible. In fact, this project is at 3 different projects, and I was able to use the KD tree for 2 of the projects that needed it, and the A-star search for another 2 projects that needed it, just to illustrate the generality of the algorithms I designed. And as well, the REPL and the GUI all work for all 3 projects, and sort of the architecture as a whole. So the main part of this project is the optimizations, the architecture, and the algorithmic complexity, as well as tests and basic software engineering skills. The GUI is not good. That wasn't the purpose of this project, and furthermore, the purpose of this project, or rather showcasing this project, wasn't to show my expertise with frameworks such as Java Spring, Django, Node.js, or different web development frameworks. And that's because I believe any software engineer with proper software engineering skills can pick up any of these frameworks very quickly. But what's hard to find is a software engineer who actually has the theoretical skills behind these applications and these different frameworks. And furthermore, this GUI, is not designed with React or whatever, or any other, front-end framework. So if you would like to see my GUI skills, you can check out other projects on my GitHub, or my experience with other frameworks such as Node.js or Django, my most popular web dev frameworks that I use. I'll provide my link to my GitHub in the description, so make sure to check those out. But this will be primarily software engineering skills focused. Now, this specific project, like I said, is actually 3 different projects. It is designed with the Java programming language. I use the Maven package manager, and I initially developed this on the Eclipse IDE, but today I'll be showing it on Visual Studio Code. So that's the end of this part. This is the stars functionality, or the celestial proximity locator. You can load in a CSV file. You can find the k nearest neighbors. either by name or by coordinate point, and then same with the radius search. So in other words, the CSV file contains coordinate points in 3 dimensions, so 3, 4, 5, and then the star's ID. So maybe it's star like ID 35, and then a name, name being optional. So what we can do is, if we, as you can see, that's not a valid file. So there's some different, error handling. Let's say we do this, load in a SQLite file. It'll say invalid header because, it can't make out the SQLite file. And if we do a real one, it'll say read however many stars from the location. Let's say we want to find 5 neighbors near the point 0, 0, 0. Okay, there's 5 neighbors. Let's say we want to find 500 neighbors around 34, 23, 2. Okay, there you go. And these are all star IDs, by the way, separated by white space. Like I said, this project was not meant for the GUI. It's just meant to demonstrate functionality. Let's go 90. We'll go 9 point here. Okay, those are the stars near whatever the hell point I typed. Now let's find, gosh, I forget the name, any names of the stars. So, is this one of the names? Star does not exist. Okay, I don't know any of the names of the stars. I'd have to look it up in the CSV file. I don't really want to do that. So let's do radius 20. We'll do 0, 0, 0. So you'll notice there's a lot more than 20, right? Because it's only how many stars within a radius of 20. So a hell of a lot. And then you could also search by name down here. And let's type in negative radius, which doesn't make sense. Okay, no answer. That there, whoops. Should be, so obviously there should be an error handler for both a negative radius that says please enter a positive radius. And I think that's implemented in the REPL, but the GUI I kind of made last minute. Now we have this one, which is the 6 degrees of Kevin Bacon. So if we load in a file path, I'm trying to remember the name. Okay, there we go. And then, all right, so we'll do, just to show you. So you could do source actor's name. So I did Kate Blanchett. Destination actor's name, Betty White. So the route to them is they co-starred in Ponyo. And then you could click here, see the filmography. Click here, see the filmography. Click on the movie, see the cast. Click back, right? All links. And then this is a small database, so it only has like 30 actors and like 20 movies or something. So, but if there were more, and you implemented a more common search where they didn't co-star in the same movie, you would have it appear on the line below. Like for example, Kate Blanchett co-starred with Betty White, and this Betty White co-starred with Arnold Schwarzenegger, and then Arnold Schwarzenegger co-starred with Robert Downey Jr. So if you entered like Robert Downey Jr. as the destination and Kate Blanchett as the source, like that's sort of how it would look. And then the GPS software, I didn't make a GUI for, so that's all in the REPL. So to show the functionality of maps, so I'll just do, so you can see I already sort of started a REPL here, just to get myself familiar with the commands I made. So let's do map this. So map boom, map set. You can see if we did some like that, it's an invalid command. And then now we want to do, so by the way, to the left of the screen is the data. There's only 6 nodes because it's, just in a test example database. So the nearest around like these latitude and longitude is node 0, so you could see with latitude 41.82, longitude that. And then let's say we want to do route, let's do node 1, so 41.8203 and negative 71.4 longitude to node 5, 41.8206, negative 71.4003. Apparently, so you go node 1 to node 2, node 2 to node 5, and there's defined ways. So if you look over here in the node, you see like these are all the possible ways from this node to this node, from this. So that's the way you would take, the shortest way. And we could do like this one up here. And then if we did route 0, 0 to 0 to 1, 0, there's no like nodes there, but the closest nodes to 0, 0 is node 0, and the closest node to 1, 0 is node 0 also. So that's why you're just getting, your starting location and ending location is the same. So it just says node 0 to node 0. And yeah, that's essentially, so we could do some other programs here. We could do the stars. So star, stars, okay, so I think it's stars. Yeah, there we go. And then, so like neighbors, 5, we want to find 5 neighbors from these points. So boom, those are the neighbors. So yeah, you could see you could run all the programs in the same REPL. And that's the functionality. Going over the overall architecture of the project. So as you can see to the left of the screen, under the Java folder, all these subfolders are different Java packages, and I'll go over each of them real quick. So we have a data retrieval package, and that basically consists of everything related to getting data and caching it, or reading it, writing it, and just some general utils. And then a graph package with vertex edges, some interfaces, and an algorithm for shortest path, a GUI, KD tree with custom heap implementation, main, and then specific maps commands and stuff specific to the GPS routing software, like stuff very specific to a GPS and what that would need. The REPL. So this is the celestial proximity locator, stars for short, because it deals with stars in the galaxy and finding distances between them, etc. So all the commands related with this. And TimDB, which is short for the 6 Degrees of Kevin Bacon project, just because it uses the IMDb database. And so all the commands and functionality associated with that. Because, although this uses a graph and the maps, or the GPS uses a KD tree and the graph, like these are general, so they are just their own packages. They could be used for any project. So, the overall sort of architecture of the GPS, or I'll do the 6 Degrees of Kevin Bacon first, is you make a request to the database for a part of the graph, or for the source node and for the destination node, just to make sure they exist. And there's appropriate error handling there. And then you start querying sections of the database, and all those queries will be cached. And you start making parts of the graph at a time, and those parts will be cached too. And then so the graph is sort of dynamically loaded. It only loads in part of the graph at a time, just because the database is too big. So it'll load in just the necessary nodes to figure out its next move. Then, hit the cache, see if the next part of the graph is available. If it's not, query it. If the query isn't available in the cache, then a real query, etc. For the GPS, it does basically the exact same thing, except source and destination nodes are a bit different. And you also have the KD tree in the GPS software. And what that does basically is it finds, nearest neighbors within or the nearest points you could go to within a certain location, like nearest places and stuff like that. And there's also SQL query caching like that. However, the KD tree is constructed not dynamically, just all at once, because it's not that big. It can just be constructed in main memory. However, a future implementation would be to make it dynamic. And then that is pretty much it. Oh, and then the celestial proximity locator, or the stars project, it basically reads in a CSV file you give it with different points. It has appropriate error handling for the CSV, and then it will use the KD tree similar to how the GPS uses it to find nearest stars within a particular radius, or just nearest stars. And technically, it works in n-dimensional space because the KD tree is general to n dimensions, but particularly 3 for the stars. Okay, that's the end of this part. In the next part, I'll be going over the specific packages. Alright, so the first package I'm going to be going over is the data retrieval package. So here I have a cache class. This is actually the only third-party API used throughout the project, and it's Google's, I'm pretty sure it's called Guava cache. And I basically use it. You can either set up a max cache size or just use the default, and you input a function. So I use Java's function utility class, and the function will basically, given a key, return a value. So it could really, this cache, isn't just a key value pair. You can have a function that does some stuff in between. So now the CSV reader just has appropriate, errors, and what it basically does is it takes in a header validator, a content validator, and these are both regex. So the header validator being the header of the CSV, making sure the header matches, and the content for each line matches. Then you have a separator, which is also going to be it doesn't have to be one character, so I know it's character separated values, but it could be multiple characters because it's a string. And then finally, you input a function that's a converter, and the converter will basically convert whatever. It'll take in a list of strings, as you see, and it'll convert it to the appropriate object that you want from the CSV file, and that should actually be an immutable list. But okay, so these are just some basically some utility functions, not that important. And then this is like sort of like a half ORM. I didn't know what ORMs were at the time, but it would have been cool to implement here. But this is just an interface for SQL databases, and then I have a specific implementation of a SQLite database with some basic functions like query, execute query that return Java objects. So I don't know. I think it would have been cool to implement norm though, so you could just call methods on Java objects and have it sort of implicitly do all these SQL statements for you, because I do have you input a little bit of SQL. But yeah, but at least you get to work with Java objects here instead of the query set that the JDBC, I'm pretty sure, package provides you after you get a SQL query set. Okay, and now let's go to the graph package, or actually I'll do the REPL package. So sort of the overall architecture, we have for REPL, you have a program. So this REPL can run multiple projects, and projects are basically programs. So for example, this project, total project, I guess, has three programs: the celestial proximity locator, the GPS routing software, and the 6 degrees of Kevin Bacon. Uh, so each of these is a program, and they each have certain commands, right? For instance, the celestial proximity locator has you load in a file. That's a command, a CSV, and it has you load in like which points you want to search through, either by name or radius. So those are commands, and it has all these commands to work with the data, and that's implemented by here a command. So it basically takes in the arguments parsed from the REPL, uh, and then returns an object. These are both interfaces, and the REPL has a appropriate error handling for different scenarios. And basically what it does is it goes through each program, then goes through each command, and when it reaches the appropriate command with the regex, it'll execute. And you can see here I'm splitting it up into tokens and doing a mutable list. And that's being passed to the execute function of the command. Now we can go to the graph. So the main part of this graph package is the asearch dynamic load. So you can pass in a function as a parameter to the class, and that will serve as the heuristic. If you don't, it, as you can see here, will just, if you pass in no parameters to the class, it's just the equivalent of making the heuristic always go to 0, which is the same as Dijkstra. And you also can pass in a comparator, which will compare two vertexes to see, if like what the appropriate edge weight is, etc. Or sorry, I should say, it is used for the priority queue in the class to see if the in order to determine the sorting sort of order of the priority queue. Okay, and then we have the actual class here. Now, for the future, I wish I would have made this. There's a concurrent version of A star search you could do that's much faster. And I also would have liked to implement a Fibonacci heap instead of the minimum priority queue I used, because I'm pretty sure a concurrent A star search with a Fibonacci heap is the fastest you can get it. And especially if it's dynamically loaded like this one is. And how I made a dynamic load or dynamically load in parts of the graph is on the vertex. I just call a get edges method, like get all the neighbors of a specific vertex, and and it uses the vertex interface. So if you're making a vertex, you have to implement this get edges method. And for both the times I use it, my specific vertex classes, they implement this and they'll check the cache first to see if there are parts of the all these edges that the A star search needs. And if it's a hit, they'll give them, and if it's not, they'll go to the SQL or whatever data source they have to get the edges. And that functionality is implemented there. So therefore, you don't need to make a graph like this. Essentially, it builds the graph as it goes, but only parts of the graph. You're not going to get a return a graph from this, of course. And then another design choice. I wish I made this an interface, and then I made this specific edge class I made, because this edge class is very general, because most edges are pretty much the same. They have a vertex, weight, destination, and then optional edge data. So you can see I just used a type T parameter, but I should have implemented an interface for an edge and then made this class as well super general. So this would be sort of the default class you could use if you didn't want to make your own edge class. And yeah, I mean, this is just basically getters and setters, overriding, compare to, equals, just the basic stuff. And also I made a shortest path algorithm interface. So
That way, if you don't like the A-star search for any of the projects that need a shortest path algorithm, they work with the shortest path algorithm interface, not specifically the A-star search. So you could use whatever shortest path algorithm you want for any of the projects. I tried to make every time I used a class, I tried to replace it with an interface instead. So, it could be the most general and extensible. You could just, change classes and not have everything break because they're just implementing interfaces. Okay, let's get into the vertex. So, yeah, this is the get edges method I was talking about. Now I can go to the KD tree. The KD tree, regarding the algorithm, there was something. Oh, so I have an interface, of course, for the KD tree, which I use throughout the project instead of my specific implementation of the KD tree. But it has basic KD tree methods, nearest neighbors, and then radius search. This file is a bit long. I wish I split it up differently, made it a bit more modular. Looking back at it, so up here is the construction of the KD tree. And I wish I would have made this concurrent version because there is an edge case in the nearest neighbors and radius search where you're going down the tree where you'll have to go down both child nodes, not just one. And so I wish I would have had a different implemented some custom algorithm where every time it needs to go down another child's or another branch of the tree, I'll just have another thread manage that, and then I would have a thread manager to make sure there wasn't a billion threads running, even though the edge cases are never that high. Then I implemented a custom heap here. This is nothing special. I just wanted to do it for fun. It's just a max heap, and then I have a heap node interface to make it a bit general. And the KD tree, forgot to mention, it uses I would say the most common version of a KD tree uses Euclidean distance to do the sorting and figure out how close one coordinate is to another coordinate. And there's also how many dimensions is the coordinate. So I made a coordinate interface, maybe a class actually. No, yeah, it's an interface. And so you can have whatever sort of dimensional coordinate you want for this KD tree. You could also have whatever comparator you want for this KD tree. Now we can go to the specific projects. So as you can see here, for example, the GPS software, I have the overall program, and it has a cache for the edges. It has a KD tree it's working with. It has a SQL database it's working with, and I just used a lot of these optional classes just to make the code a bit more attainable. Not always have to check for nulls every time I'm doing something or have null pointer exceptions. So I just tried to work pretty much everything in terms of optionals. So it would force me to get a compile time error. The IDE would let me know it's an optional, and I would have to check if it's empty. And as you could see, if any of this doesn't make sense, I have I have a lot of documentation explaining it all. And then so the constructor, you're making all the different commands and putting in the appropriate regex. So these static variables right here are just regex, which you can see in the maps utils. So you can see all the regex for the different commands. And these are just some general things that are used a lot. So a lot of times you have to find the traversable nodes because not all, according to the specs of the project, not all nodes can be traversed in terms of points in the GPS data that I was working with. So you had to check if it was traversable. And yeah, let's see here. So pretty much basic, just getters and setters. And then, each command. Oh yeah, another design choice. I tried to make almost every class as I could. Like all the commands are final. It just doesn't really make sense to, have other classes inherit from them. And just basic coding Java practices. Try and make everything final. Try and make all the classes immutable. Um, Work with interfaces. So most of these execute methods are pretty simple. Mainly this one just loads in a database, so it just uses the setter. But a more complex command like nearest command, or how about I'll do the route node command, and that basically just, I'm pretty sure, has a source and a destination. It just executes the shortest path algorithm. So you can see there's a lot of parsing that has to be done from the string, from the REPL, or from the GUI, whatever. It works with both. And got to find if they're even traversable, and then if they're not, you're just finding the nearest traversable node from the source and destination to work with. Then you use whatever shortest path algorithm the program is using. So I used A-star search in this case. And yeah, handle the appropriate cases. So that's basically, the structure here. The main points were, for every class I tried to have an interface. Every time I could make something immutable, final, I did it. I tried to handle errors every possible case. And the testing really helped me with this because there are so many tests, and I'll cover those in the next part. And I'll start with the graph package tests. Most of these read like English, so it should be pretty self-explanatory. So of course, sadly, I had to make a testing vertex, and then I had to populate a graph. So I made different edges, different vertexes, and then to set up, I had to basically add different edges to different vertexes to make the graph complete. And then you have your base case, a path from one node to itself. Where the path is, not always the next best edge, is what works the most. So in other words, if you were just greedy the whole time, it wouldn't work. There's something that is short or is long and not the best, but it ends up being the best in the long run. Okay, and then I made some general tests. So obviously this. I think this needs a bit more work. Luckily, there's not too many edge cases in shortest path, especially when you're dealing with not something like the Bellman-Ford algorithm where you're working with negatives, negative edge weights and stuff, so you have to worry about cycles. But when you're just working with positive stuff, most of the errors, or most of the edge cases, are really just going to be stuff not in the domain, like a negative number for an edge, and basically just testing error handling at this point. So that's something I wish I added, is some more testing, not per se for the functionality, but for the appropriate error messages I would get. KD tree tests. Let's see here. So we have, and I just made my own CSV files to test it out, and then some max heap tests, and basically almost for every class there's a corresponding tests, and then the system tests you can find in system tests right there, and there's many of these, and they or the integration tests. CS32 test. This Python file is you can read it if you want. It's basically how the tests are run, and from there you could sort of parse how to write a test. But it's pretty much just input label, output label, and end it, and that's what you expect. So this would basically be 5 different commands into the REPL. And sadly, I didn't make it so you could put comments in these files. But